I'm delighted to have you as part of this community. Welcome, welcome, welcome. It's a pleasure to have you join us as we uncover the secrets of purity quantum mechanics. In quantum mechanics, and especially quantum information theory, the purity of a normalized quantum state is a scalar defined as Tra is the density matrix of the state and Tra is the trace operation. The purity defines a measure on quantum states, giving information on how much a state is mixed. Let's now venture into the realm of mathematical properties and explore the fascinating intricacies it holds. The purity of a normalized quantum state satisfies our fractal analog, where D is the dimension of the Hilbert space upon which the state is defined. The upper bound is obtained by Tra1 and Tra-C trace. If is a projection, which defines a pure state, then the upper bound is saturated, Tra1C projections. The lower bound is obtained by the completely mixed state, represented by the matrix Alfract ID. The purity of a quantum state is conserved under unitary transformations acting on the density matrix in the form UU, where is a unitary matrix. Specifically, it is conserved under the time evolution operator at E frac I bar at T, where is the Hamiltonian operator. Welcome to the next segment, where we explore physical meaning and its significance in our journey. A pure quantum state can be represented as a single vector in the Hilbert space. In the density matrix formulation, a pure state is represented by the matrix pure. However, a mixed state cannot be represented this way, and instead is represented by a convex combination of pure states mixed I, while I1 for normalization. The purity parameter is related to the coefficients. If only one coefficient is equal to 1, the state is pure. Indeed, the purity is when the state is completely mixed. That is, it is completely mixed frac some I'd say angle ci frac 1 did, where I are orthonormal vectors that constitute the basis of the Hilbert space. As we venture forward, let's examine geometrical representation in detail and gain a deeper appreciation for its significance. On the block sphere, pure states are represented by a point on the surface of the sphere, whereas mixed states are represented by an interior point. Thus, the purity of a state can be visualized as the degree to which the point is close to the surface of the sphere. For example, the completely mixed state of a single qubit frac 1 to I is represented by the center of the sphere, I symmetry. A graphical intuition of purity may be gained by looking at the relation between the density matrix and the block sphere, rho for curl left a math for total symbol sigma right, where is the vector representing the quantum state on or inside the sphere, and x, y, z is the vector of the Pauli matrices. Since Pauli matrices are traceless, it still holds that. However, by virtue of ab iob, a ho for curl left hence e operator and traho frac 1 plus a, which agrees with the fact that only states on the surface of the sphere itself are pure I1. Brace yourselves for the next chapter, where we'll be dissecting linear entropy. Purity is trivially related to the linear entropy SL of a state by 1 SL. The linear entropy is a lower approximation to the von Neumann entropy S, which is defined as stot operator and trahol naho equal angle naho wrangle. The linear entropy then is obtained by expanding around a pure state, that is, expanding in terms of the non-negative matrix in the formal Mercator series for the logarithm angle naho wrangle equal angle 1 rho wrangle frac 1 angle 1 ho wrangle frac 1 angle 1 ho wrangle dots, and retaining just the leading term. Both the linear and the von Neumann entropy measure the degree of mixing of a state, although the linear entropy is easier to calculate, as it does not require diagonalization of the density matrix. Some authors define linear entropy with a different normalization S lot for 1 operator and traho, which ensures that the quantity ranges from 0 to unity. As we transition to the next segment, let's unravel the mysteries surrounding entanglement and gain a fresh perspective. A 2-qubits pure state ABHB can be written using Schmidt decomposition as ABHB, where J, JB are the bases of H, HB respectively, and Ch1, J0. Its density matrix is a by Chi G, B. The degree in which it is entangled is related to the purity of the states of its subsystems, and similarly for see partial trace. If this initial state is separable, i.e. there's only a single J0, then are both pure. Otherwise, this state is entangled and are both mixed. For example, if angle a fire angle a fracas angle O times angle B plus angle O times angle B, which is a maximally entangled state, then are both completely mixed. For two qubits pure or mixed states, the Schmidt number of Schmidt coefficients is at most 2. Using this and Peer-Szyrodecki criterion for two qubits, a state is entangled if its partial transpose has at least one negative eigenvalue. Using the Schmidt coefficients from above, the negative eigenvalue is. The negativity of this eigenvalue is also used as a measure of entanglement. The state is more entangled as this eigenvalue is more negative up to ifrac 1 for Bell states. For the state of subsystem similarly for B, it holds that ABR, and the purity is 1. One can see that the more entangled the composite state is, i.e. more negative, the less pure the subsystem state. In this part of the video, we'll be delving deeper into inverse participation ratio IPR and analyzing its key components. Inverse participation ratio IPR. In the context of localization, a quantity closely related to the purity, the so-called inverse participation ratio IPR turns out to be useful. It is defined as the integral or sum for finite system size over the square of the density in some space, e.g., real space, momentum space, or even phase space, where the densities would be the square of the real space wave function x, the square of the momentum space wave function erg, or some phase space density like the Husserl distribution, respectively. The smallest value of the IPR corresponds to a fully delocalized state, ipsix certain for a system of size n, where the IPR yields xn n. Values of the IPR close to 1 correspond to localized states, pure states in the analogy, as can be seen with the perfectly localized state xx, where the IPR yields x1. In one dimension, IPR is directly proportional to the inverse of the localization length, i.e., the size of the region over which a state is localized. Localized and delocalized extended states in the framework of condensed matter physics then correspond to insulating and metallic states, respectively. If one imagines an electron on a lattice not being able to move in the crystal localized wave function, IPR is close to 1, or being able to move extended state, IPR is close to 0. In the context of localization, it is often not necessary to know the wave function itself. It often suffices to know the localization properties. This is why the IPR is useful in this context. The IPR basically takes the full information about a quantum system, the wave function. For our n-dimensional Hilbert space, one would have to store north values, the components of the wave function, and compresses it into one single number that then only contains some information about the localization properties of the state. Even though these two examples of a perfectly localized and a perfectly delocalized state were only shown for the real space wave function and correspondingly for the real space IPR, one could obviously extend the idea to momentum space and even phase space. The IPR then gives some information about the localization in the space at consideration. E.g., a plane wave would be strongly delocalized in real space, but its Fourier transform then is strongly localized. So here the real space IPR would be close to 0 and the momentum space IPR would be close to 1. Leave a comment below and let me know what you thought of this video.